Hello and welcome to today's 10-minute talk, which we're going to do on neurology. Hopefully trying to keep it quite simple, go through some of the difficult terminology and help with your understanding. Our aims for the session should be that we'll go through a really little bit of the neuroanatomy, think about what our nervous system does, go into synapses and neurotransmitters, and discuss upper versus lower motor neurons. These are things which may well be coming up in your classes. I sincerely hope you find it interesting, and as usual, any questions, please don't hesitate to let me know. First of all then, the simplest part of neuroanatomy. When people talk about the central nervous system, what they're talking about is the brain and the spinal cord, nothing else. When we talk about the central nervous system and the peripheral nervous system, what we're doing is we're thinking about the entirety of the nervous system. We've got our central nervous system there, which is the brain and spinal cord, and the peripheral nervous system, which is everything else. This is made up of hundreds of nerves, and each nerve is made up of lots of neurons. And a neuron is a single nerve cell, so in total our body is made up of billions of neurons. Our central nervous system and peripheral nervous system are an anatomical description. That means that they're entirely based on the anatomy, that, as I've said already, CNS is brain and spinal cord, and peripheral nervous system is the rest. It does also then get broken down into the autonomic nervous system, first of all, which is effectively what the CNS and peripheral nervous system can do. This is a functional name, okay? So it's about what the nerves are doing rather than where they are. If you imagine the nerve tissue there supplying, as you can see in my drawing, a muscle tissue, and another nerve supplying maybe what might be the gallbladder down there. We have to think about the autonomic nervous system performing the actions that the body does unconsciously. Okay, so things like your gallbladder contracting, that gets done by our nerves, and we don't do it consciously, so that's performed by the autonomic nervous system. For everything else that we consciously do, like contracting our bicep muscle, for example, we might do that consciously, so we will refer to that as the somatic nervous system. Autonomic nervous system is often then categorized down further into the sympathetic responses and the parasympathetic responses, and also into the enteric nervous system. So sympathetic, first of all, often gets called fight or flight, which effectively means that you see a lion and your pupils dilate, your heart rate increases, your blood will divert to skeletal muscle, blood gets removed from the skin and the GI tract, your heart contractility improves, digestion gets paused so that we can use all of our muscles and our eyesight and our heart to run away or to fight. This can obviously not happen. This doesn't just have to happen with lions, it happens with all sorts of other things. It might happen in exam halls or in many other situations I'm sure you're aware of. Parasympathetic nervous system, also known as the rest and digest or feed and breed, is exactly as you'd expect. It's when we need to increase blood flow to the GI tract, such as when you have a McDonald's meal or it's Christmas time and the family are all around. We need to be digesting and resting to remove all of the nutrients from the feed that we are scanning. Our pupils can contract to allow closer vision. We increase salivary gland activity and peristalsis. Our heart rate slows. It's also involved with stimulating sexual arousal. And this very, unhelpful acronym SLUD, sex, salivation, lacrimation, urination, digestion and defecation, help you to remember what the parasympathetic nervous system does, if you like that kind of thing. I'll never remember SLUD though, to be honest. Briefly to mention then this enteric nervous system that I've mentioned. It's an emerging science. We recognise that there's more nerves in your guts than there are in your brain, but more than that, I'm not really all that confident, to be honest. We know that the enteric nervous system senses chemical and mechanical changes in the gut, regulates secretions and modulates peristalsis. But there are certain fields that are emerging now which suggest that it could be doing a lot more. There's lots of interesting science currently around if our enteric nervous system is in charge of our mood or our mental health. There are groups who are testing the microbiome, effectively all of the bacteria that make up our guts, and how that plays with our enteric nerves, and how that then affects everything about our personality and our future. People often equate it to things like IQ and, like I say, mental health, but there's no strong evidence there behind it. There's more groups starting to capsulize things like fecal microbiomes of a healthy person, and the theory being if you take it as an unhealthy person, does that then fix your symptoms? But, watch this space and do some research, enjoy learning about these new trends which are happening currently. So, very briefly, synapses and neurotransmitters. Effectively, how do all of these nerves communicate? Because, like I've said, there's billions of them there, and they need to communicate effectively for us to do everything you're doing right now, from learning, from looking, hopefully listening. Your nerves are doing all of that, and there's billions of them, so they need to effectively communicate perfectly every time. And as you can see here from my very dodgy drawing, there is a gap in between the nerve cells. This is known as the synapse, and across this gap neurotransmitters can move from one nerve cell to another. It's unknown how many neurotransmitters that there are. Examples that you'll know will be things like acetylcholine, GABA, serotonin, glutamate, dopamine, ATP, nitric oxide. The list goes on and on and on and on. And effectively, you can see here on the yellow surface of the nerve cell, this is where the nerve impulse may be arriving. At that point there is where neurotransmitters will be then encouraged to be produced. They will then transfer across the synapse, and then they'll be received at the green side on the other nerve cell, where the arrival of that neurotransmitter will stimulate some kind of response and send that response down the nerve cell further. There's any number of different possibilities that can occur, and even the absence of a neurotransmitter arriving at the green cell side of the nerve there may well stimulate a response. Effectively, this is how our body functions. Why care? The example here I'm giving is a patient arrives with paralysis of one part of their body. We can use our knowledge of the nervous system to tell where the lesion is. We use this word lesion fairly frequently in neurology. Effectively, that encompasses things like stroke, if there's a bleed there that's damaged the nerve cell, or if there's a tumour there that's damaging the nerve cell, if there's an interruption in the nerve's ability to transfer its information, such as if it's broken, or if there's damage to the bone nearby. You can have any number of reasons why the nerve cell is damaged, so we just use the word lesion to encapsulate all of those things. For example, then, if this patient is paralysed in one part of the body, we don't know if it's damage to the part of their brain that controls the arm movement, or it's because of a damage between the nerves from the spine to the nerves in the actual arm that then caused this patient to have the inability to move it. We're thinking, is it a brain / spinal cord thing, which we call an upper motor neuron lesion? Or is it a nerve problem outside of the CNS, which we call a lower motor neuron lesion? Again, these terms upper and lower motor neurons get very frequently used. They are, again, part of a very anatomical, descriptive use, because they're describing either a CNS or a PNS lesion. So here's how I remember the difference between upper versus lower motor neurons. I use the phrase, when the parents are away, then the kids will play. I.e. the parents being the central nervous system, the brain and spinal cord, providing all of the messages to the peripheral nervous system, i.e. the kids. If the injury is in the central nervous system, i.e. the parent, then the kids, the peripheral nervous system, will be lacking in controlling messages. For example, in an upper motor neuron problem, you'll usually have hypertonia and spasticity, like jerky, over-caffeinated, over-controlling parents, i.e. the parents are not in control, they are unable to handle the peripheral nervous system, the body then is constantly in this heightened state of hypertonia and spasticity. If there's a lower motor neuron problem, then it usually involves hypotonia and flaccid paralysis, like an injured child lying on the floor. Hope that helps. As before, you can see in upper, you've got increased tone, exaggerated reflexes in such conditions such as stroke, multiple sclerosis, MND, or in a lower motor neuron lesion, you've got decreased tone, reduced absent reflexes, wasted muscles, such as in peripheral nerve trauma, MND as well, Guillain-Barré syndrome. Here's an important case where upper versus lower motor neuron becomes very important. The cases of a Bell's palsy, which you might have heard of. Now, in a Bell's palsy, what you have is the whole side of the face is paralysed, including the forehead. And often loss of taste in the tip of the tongue is reported because the anterior 2/3 of the tongue is innervated by the facial nerve. It's a lower motor neuron lesion then, because the facial nerve obviously isn't part of the central nervous system. It's idiopathic and it can affect teenagers, and usually is reported to have 20 cases per every 100,000 people. So you usually do see one in paediatrics maybe every year or so. The important feature is that if only the lower half of the face is affected, then it can't just be the facial nerve. Okay, so if they can raise their eyebrows, if their forehead is not being affected, then you need to think of an upper motor neuron lesion, such as a stroke. Okay, so facial nerve palsy would have a full side of the face being affected, including the forehead, whereas a stroke, often you would just see the lower half of the face being affected. In summary, terminology can be confusing, except that it always was for me in medical school. I like to think of anatomically, the CNS and the PNS are separate, and functionally we think of the autonomic nervous system and the somatic nervous system. Upper and lower is the same as CNS and PNS. It's helpful in allowing us to find out where the problem is, and neurotransmitters make it all happen. We don't know everything about them yet.